All right, let's talk about something that's absolutely fundamental in computer science. We're diving into hash tables. Specifically, what in the world do you do when two different pieces of data try to claim the exact same spot? Getting this right, well, it's the difference between a system that flies and one that crawls.
So it all boils down to this one simple question. You've got this awesome hash function, right? It takes a key, like a username, and instantly tells you exactly where to store that user's data in an array. It's super fast. But what if it tells two different usernames to go to the very same spot? Yep, that's what we call a collision. And here's the key thing to get. A collision isn't a mistake, it's not a bug. It's just a normal, expected thing that happens. But how you decide to handle these collisions, that's what separates a good hash table from a great one.
And I mean everything. The strategy you pick has a huge impact on your system speed, how much memory it uses, and even how complicated your code gets. So let's jump in and look at the two main ways people solve this.
Okay, so we're going to break down the two big strategies here. They're called chaining and open addressing. And to make it all make sense, we're going to use one simple analogy that's going to make it all just click.
So I want you to picture this in your head, a long row of mailboxes. Your hash function, it's like a helpful postal clerk. You hand it a letter, your piece of data, and the clerk instantly points you to the exact mailbox it belongs in. Simple, right? But what if you get to that mailbox and it's already full?
And this is where our two solutions take completely different paths. On the left, we have chaining. With this approach, you just open up the full mailbox and stick your new letter into a folder right there inside it. Easy. But on the right, we have open addressing. Here, you can't share. So if your mailbox is full, you have to find another one. The rule is simple. Just check the next one down the line, and the next, until you find an empty slot.
So let's put the official name on that first idea. That folders and mailboxes approach is called separate chaining. It just means that every slot in our hash table isn't just a single spot. It's a bucket, usually a linked list, that can hold multiple items. A collision happens? No problem. Just add the new item to the bucket.
And that check the next mailbox strategy, we call that open addressing. Here, everything, all your data, has to live inside the main array. There are no buckets, no folders. When a collision happens, you have to probe, which is just a fancy word for check, the next slots in a sequence until you find an open one.
Okay, so we get the basic ideas. But now for the important part, the performance. Which one's faster? Which one uses less memory? It turns out the answer to both of those questions really depends on one single critical number.
And that number is called the load factor. You'll see it represented by the Greek letter alpha. All it is a simple ratio. The number of items you've stored divided by the total number of slots available. Think of it as how full your hash table is. This one little number is the king. It controls everything about performance.
So this table really lays out the big trade-offs. Let's look at search time. With chaining, the time just grows nicely with the load factor, alpha. But look at open addressing. As alpha gets close to 1, meaning the table is almost full, that search time blows up. It gets really, really slow. For space, open addressing wins. It's leaner. Chaining needs extra space for all those little buckets. And finally, look at deletion. Super simple in chaining. But for open addressing, yeah, it's a known headache.
So here's a golden rule for any software engineer. If you want your hash table to stay screaming fast, to keep that awesome constant time performance, you have to keep your load factor below a certain point. A good rule of thumb is about 0.7. Once you get more full than that, it's time to resize the whole table to bring alpha back down.
All right, so both methods sound pretty good when everything is working perfectly. But what happens when things go wrong? Let's dive into some of the hidden dangers, the common traps that can really mess up your performance. This is chaining's absolute worst nightmare. Imagine you have a really, really bad hash function. It just keeps sending every single key you have to the exact same bucket. All of a sudden, your super efficient hash table, as you can see here, is basically just one giant linked list. And your search time just tanks from nearly instant to painfully slow.
Now, open addressing has its own boogeyman, and it's called primary clustering. Here's what happens. A key hashes to a full slot. So you check the next one, but it's full too, from a previous collision. And the next one is full. You end up creating these long, continuous chains of occupied slots. And these clusters are just brutal for performance. Every new search or insertion that lands there has to walk that whole long chain.
And remember, we said deletion was complicated? Well, here's why. With open addressing, you can't just find an item and delete it, leaving an empty space. Why not? Because that would break the probe chain for other keys that might have landed there and had to keep searching. The fix is kind of a hack. You use something called a tombstone. It's a special marker that says, hey, something used to be here, but it's gone now. Keep looking. It works, but it adds a lot of extra complexity.
So, after all of that, with all these trade-offs and hidden dangers, how in the world do you actually make the right choice for your project? Let's boil it all down to some clear, practical advice.
You're going to want to lean towards chaining when you need something really robust. It's much more forgiving if your hash function isn't perfect. Deletions are a piece of cake, which can be a huge win. And it's also great when you have no idea how many things you're going to end up storing, because those buckets can just keep growing. Basically, if you value simplicity and safety over squeezing out every last byte of memory, chaining is your friend.
On the other hand, you should reach for open addressing when memory is super tight and performance is absolutely critical. Because all the data is packed together in one array, it can be way faster thanks to how CPUs cache memory. But, and this is a big but, this is only a good choice if you are confident you have a high-quality hash function and you know you can keep that load factor low.
So look, if you only remember one thing from all of this, let it be this. Collisions aren't your enemy. They're just a fact of life in hash table land. The real game, the art of building a high-performance system, is all about being obsessed with managing that load factor. You keep alpha low, and your table will be blazing fast, period.
And I'll leave you with a little puzzle to think about, a classic engineering trade-off. Imagine you're in a situation where your memory budget is tiny, you have to be as efficient as possible, but you've got a bad feeling that your hash function might not be that great. So, what do you pick? What are the risks you're willing to take? Something to chew on. Thanks for joining me.